All right, everyone, welcome back. We are now officially in Unit 2, resetting the lessons. Now we're back to Lesson 1, or Lesson 2.1. And this is going to be a pretty long and extensive lesson. And it will be building upon nodal analysis, loop analysis, KVL, KCL, all of the cool stuff that we learned in the previous unit. So let's just get into it. So we have two new terms. We have the Thevenin voltage and the Norton equivalent, or Norton current. And basically, this dude named Thevenin, I don't really know anything about him, but basically, he said that if you have two networks and you have one of the networks and it has like resistors and current sources and basically linear devices, then you can simplify it down to one resistor, which is R equivalent, which we learned about ways to find R equivalent in the last unit, and a Thevenin voltage. Okay, so just one voltage source can represent all of the sources that are in this linear circuit. So right here, I've just written down, replaces an entire linear circuit with one voltage source, V Thevenin. And then the Norton equivalent is just the current version. So you can have like a single current source rather than a voltage source. And so replaces an entire linear circuit with one current source, IN. So this is kind of what it looks like. You just have this random network right here. And this random network can be anything, right? Anything that is connected to this guy right here. And pretend that this was another network that's been simplified down into one V Thevenin. Okay? So as long as the system is linear, the combinations can be very complex. So you can have, like, we solved a bunch of nodal analysis, loop analysis systems or circuits, and those things are going to be connected to some random network, right? Now, you really want to know how to solve for V Thevenin, right? So the first thing you're going to do is just disconnect the circuit that you wish to analyze from the rest of the network. So basically, we're just going to take a bunch of pliers, or take a pair of pliers and just cut it, right? And the network will be disconnected from the circuit that we want to analyze. And then we're going to find the voltage difference between the network terminals. So when we cut this guy up, right? Oops, that's not straight. When we cut this guy up, we're just going to have the terminal A and the terminal B, and we have to find the voltage difference between these guys. So effectively, you could think of it as like some battery between the two, right? And this battery is just the entirety of the other network. Okay? And now you can safely analyze this. Now, how do we find R equivalent? So we were able to find R equivalent in purely resistive circuits with just one power source and a bunch of resistors. But now, what if this network that we wish to analyze, this box right here, actually had multiple power sources, multiple current sources, and stuff like that? You can't just apply our parallel and series stuff yet, okay? So you have to actually remove the voltage sources and remove the current sources. And I don't really know the theory behind this. I'm just telling you how to do it. So we're going to remove all the voltage sources and replace them with short circuits. So a short circuit is just a pure wire, okay? Theoretically, no resistance. And then for a current source, we're going to replace it with an open circuit. And this is theoretically infinite resistance, okay? Like so. And then to find I Norton, or current Norton, then you're just going to use Ohm's law. And we're going to get that V Thevenin is equal to I Norton times the R equivalent, and I Norton is equal to V Thevenin and R equivalent. Now, the thing is, you can find you can find the I Norton first and then find the V Thevenin, but I've found it easier to just do V Thevenin first because it just requires some kind of a nodal analysis. And if you really needed to use a loop analysis, then you would rather want to find a voltage across the terminals. Okay, so all of that was pretty abstract, so let's go ahead and do a practice problem. All right, here's the first practice problem. So let's just go ahead and do it. So we have a network here attached to this circuit, right? Looks pretty familiar to what we've been doing. Now we want to find the V Thevenin, the I Norton, and the R equivalent. So we're first going to disconnect the network. And we're going to analyze the other network, this network right here. Okay? So we're just going to go ahead and copy and paste this. And just straight up delete all of this. Okay? So we're left with this right here. Now, to find the V Thevenin, right, it's just the voltage difference between the terminals. So it's just this right here, VAB. Okay, but I'm going to call it VS for simplicity's sake. And you can actually treat this, what I like to do is treat it like a battery, okay, or some kind of power source that we're trying to find. But you need to know that this is a network, okay? It's just that all of this voltage in this random network condenses down to a V Thevenin, which is shared with this network right here. Okay. So how are we going to find VS right here? Okay. Well, we have a ton of different methods, right? And I said that this would be coming back, but how do you think that we would find it? Well, we would use a nodal analysis, right? Because we want to find some voltage right here. So hopefully you guys know how to do a nodal analysis really well. The first thing that we're going to do is identify the nodes that we want to look at. So we have a node right here, and right here, here, and here. Now the question is, do we need to write a nodal equation for every single one of these? No, because I can see that this guy right here is just 0 volts because it's this whole thing right here is a node. Okay, we learned that in last unit, but we don't know this node right here, so we'll call it V1. We also don't know this node right here, we'll call it V2, and 2 right here, and we don't know this one right here, N3. In fact, this is the one that we're looking for. It's N3. Now, I'm sure that there are other ways of doing this, but I think that this is the simplest way because I naturally like nodal analysis. You can definitely solve it with a loop analysis, but remember that you're going to be making loops like this, and the expectation is that you are going to find a voltage, okay? Or you can find the current. All right. Anyway, I'm going to be doing these with nodal analysis. All right, so let's go ahead and write these nodes down. So for node 1, we have V1 minus V2 over 2 plus V1 minus 0 over 4, because we're doing this right here, just to freshen up again. And if you haven't watched the video lectures on nodal analysis or loop analysis, etc., I would highly encourage you guys to do that. I do a lot of different idiosyncrasies, and like for example, I count all the currents going outwards as being positive, and I'm just going to be doing this like straight up. So if you haven't watched them, then I would highly encourage you to go and watch those videos. And we have V1 minus Vs over 1 equals 0. Okay, we're going to go ahead and solve it out. Or expand it. Or simplify it, sorry. Just saying random words. And there we go. We have 7v1 minus 2v2 minus 4vs equals 0. Now we're going to do node 2. And right here we have v2 minus v1 over 2, v2 minus 3 over 6, and we have negative 2 going into the node. So v2 minus v1 over 2 plus v2 minus 3 over 6 minus 2 amps equals 0. We're going to go ahead and simplify. And we're left with negative 3v1 plus 4v2 equals 15. Now we have n3 for our third equation because we have 3 unknowns. And that is going to be simply Vs minus V1 over 1 equals 0. And notice, we get that Vs is equal to V1. Okay? So that means that we kind of just proved that when you have this like circuit right here, remember that we just cut off the network. So technically, this is another way to look at it. Technically, this has no current going through it right now, right? Because it's been disconnected. Okay, because we're looking at this as a network independent of the other network. So then that means if there's no current through this, then this guy right here, it's all going to be like the same node. Okay. The voltage difference between them are the same, is basically what I'm trying to say. So if you want to simplify it like that, you can technically just put A and B right here. But I did that because it's easier for me to think of it like this. Okay. Let's go ahead and move these guys up here. I'm going to go ahead and plug in Vs to be V1. I'm going to plug V1 to be Vs, and we'll just solve for V1. And if we go ahead and put this into the calculator, we're going to get that V1 is equal to 5, V2 is equal to 15 over 2 volts, and therefore V Thevenin is equal to 5 volts. So this right here is 5 volts. And so between this network and this network, we have a voltage difference of 5 volts, and that is V Thevenin. Okay? So let's circle that or box it in. And you can go ahead and check it. I've already checked these problems, but I would highly encourage you guys to check it and see if there's any mistakes. It's good practice for you guys. So the next thing we're going to do is find our equivalent. So once again, we're going to grab the same network, and we're going to, and we are going to disconnect the network. But this time, we are going to also remove all of these sources, okay? Because we want to find the R equivalent. So what did we say? Current sources produce an open source, okay? So, an open circuit. So this was a current source. In finding R equivalent, we're going to replace that guy with an open circuit. Now, the voltage source we are going to replace with a closed circuit. Okay? And we are going to solve for the R equivalent in this way. Now, this is a much easier problem. We can simply just do, we can add these guys up because they are in series. So we have 2 plus 6 equals 8. And then we can take that configuration and put those guys in parallel. And it will be 8 is in parallel with 4 over 8 plus 4. Okay, so these guys are now in parallel, and we are going to go ahead and plug this into the calculator. Sorry, these aren't. It's multiply. And we get 8 over 3. And then we are going to put that configuration to parallel, into series. So 8 thirds plus 1 equals 11 thirds ohms. And that is the R equivalent. And finally, we are going to find the I Norton. And that would just simply be the V Thevenin over the R equivalent, which is equal to 5 over 11 thirds, or 15/11 amps. And that's it. So I think I'm going to end this right now, and just have you guys to digest this. We're going to do some more practice problems sometime. But yeah.